Well, good evening, everyone, and welcome to the second week class. It only gets better from here on out. It gets a little harder, but not terribly hard. We're going to start on chapter 2. I'm going to discuss chapter 2. And chapter 2, I might as well share this screen with you, the book itself. Oh, wait, how many people have their book already? I'll go down the list. I think I got, there we go. Where did my list go? Oh, that was real nice to me. Oh, it's not going to give me everybody. Okay. All right, I'll have to do this impromptu. Mike, do you have a copy of the book yet?
Yes, have the spiral bound paper.
Jeff, did you get a copy yet?
Got mine.
Perfect. Jason?
I got mine.
And who's left?
Kathy.
Can't
And
see
yes, I
everybody.
have
good.
the Kindle one.
Follow along with me the best you can. Keep in mind that my pages may not line up with yours, but I'll do the best we do the best we can. It is the same material. It's just the way it's organized. The way the pages are split up are set for viewing on a computer screen on the Kindle version, which I use for the class. Only because holding up the pages to the camera and flipping them page by page through didn't work out too well. People were complaining that my hand was too shaky. I actually did not try that. I'm only kidding everybody. Here we go. Chapter 2. In this chapter, you'll learn about radio spectrum, radio signals and waves, the characteristics of radio signals, names and types of radio equipment, and simple radio stations. Well, I hope we'll go a little beyond that, because otherwise I'm pretty much useless. Okay. I asked you guys to try to read this, but I figure that maybe you haven't read it all. Not a big deal. This is not a crucial chapter in terms of the information it covers. It's pretty well repetitive. Much of it's repetitive of the technician class. Okay, radio signals and waves. Okay. They give a fair description of how radio waves work in this book, a little better than the technician book. I hope they kind of make it easier to understand for you. The book begins by telling you that a radio signal is basically an emitted wave or a radiated wave, and it gives you some rough definitions and explanations. I'm going to unshare this for a moment. Gosh, I lost my screen for that. Where did it go? All right, something here is not right. Let's see, here we go. Nope, that's not it. Must be hidden somewhere back in here. There it is. We'll stop share for a second. And I want to pull up another share. In order to do that, I have to open a file. So I'm going to talk to you a little bit while I do that. It's a complex thing to envision, and it takes a little catching on, I guess, what a radio wave really is. So I'm going to review a few things which will help make it a little easier to understand. Whenever electrical current travels through a wire, it drags along that wire not only the flow of electrons, but as the electrons flow, they create a magnetic field at right angles, which wraps around the flow. So as it's going down the wire, it makes a magnetic field around itself. If you'd ever done this as a kid, it is a principle of which an electromagnet works. is a principle which basically a relay works, and it's a principle of basically how a transformer works. Now, a transformer only works in AC current. Well, I'll discuss that a little bit later. And radio waves are an AC current. They're closer to the transformer. But we're going to start a little simpler than that. I've got to go to ham radio class, and I've got to look for a file for you while I'm talking. Okay. Radio waves are the culmination of the electrical component and the magnetic component of the electromagnetic phenomena. Because they are a wave, they are an AC current, so they are an electromagnetic waveform. Now, here's the part that's hard to explain to you. No magnetism exists without electricity, and no electricity exists without magnetism. So whenever you have a magnet present, the reason magnets that are fixed magnets work is because they have they're made of a metal where the electrons align in such a way that the electrons are all in one orientation. Think of it, although it's not true, I don't have the drawing, so I'm going to have to make you one. All right, we'll do this as we go. I thought I had a drawing from the last class. Okay. Oh, you guys are the technician class. I'm sorry, I stand corrected on what I said earlier. I'm getting my classes mixed up. All right, I'm going to share with you guys. Share a screen. And this is it, I think. In a fixed magnet, come on, screen, open. That's not the screen I want. Oh, do I have one open? Yes, I do. So let's see what that screen looks like. Okay, let's get this one. Sorry for a little bit of a delay here, guys. I always have problems with, here we go. We just take untitled paint. That's what we want. Share. All right, here we go. Now, and in a conventional magnet, a fixed magnet, we have you're being uncooperative. Well, imagine that this box is a magnet. What happens is we get electrons to kind of all stack up on one side and basically, this is not going to work the way I want it to. Basically, we get a positive charge, a bunch of positive charges on the other side. Not exactly, but this is a crude way to think of it, okay? What we get is we get them oriented in their molecular structures in a pattern. And so we define that creates a north side of the magnet and a south side of the magnet. Let's go back one. Now, you all know if you put a north magnet to a north magnet, it will push away, and you put a north magnet to a south, it will pull to each other. This happens because, and this I got to draw the best I can for you. There are lines of, that's not going to work. Got to go the other way. There are lines of flux. That are going around the magnet. These are actual lines. Oh, this one goes backwards. These go back, they go basically encircle the magnet. And these lines of flux are actually lines of electromagnetic force. Electrons lined up inside the molecular structure of the material, and only certain materials will do this, iron being one of them. Of course, things like steel, which have iron in them, are one. Now, all metals will allow the flow of electrons, but they don't all have them lined up in a way to create their own magnetic field. This flow of electrons, or this field of electrons, when it moves, this field of magnetism, when it moves, when in the proximity of a piece of metal. So let's introduce another little box here. I'll make this into a little thin piece of metal. If this magnet moves, or if this field moves, the little electrons inside the metal get pulled back and forth by the field created by the magnet, and the electrons flow. This is the mechanical process of mechanical induced induction. Now, I'm going to do a new drawing for you for a minute. Let's see that. Now, what happens in a radio wave is easier to understand if we look at a transformer, because it's the same action, a little different. In a transformer, we put a coil on one side. Then we put a coil on the other side. And magically, AC current coming in here comes out here. Now, just so you know, we put a couple of lines in here when we draw a transformer, because most transformers have an iron core that makes the transfer of magnetic fields more efficient, but it can be an air core as well. It's just not quite as efficient. The way this works is when electrons are moving through this circuit, they make a magnetic field which wraps around this one, if you will. I'm trying to draw that, but it's not the greatest. And when it does, it makes electrons flow through this side, assuming there's some closed circuit for it to go through, which I didn't do, but we will if we like. Put a little light bulb in here. Okay, so it looks like a daisy. Give me a break. Now, what happens in a radio transmitter is we have this same transformer. It's just way bigger. We have this primary side, which is the transmitter sending a signal out right here, going through the wire. And this wire I'm not drawing this real well, but this wire is our antenna. So imagine the signal is going out to the antenna. This wave, this lines of magnetic flux, this is going just like I'm showing you out into the air. And somewhere in that air, we got an antenna. That antenna, come on. Won't switch colors to save my butt today. That antenna is getting, imagine this whole thing is the antenna, folks. That antenna is getting those magnetic waves. Now, that magnetic wave is very, very tiny. And we send that signal into the radio, a detector circuit. Just put a block in here. We'll call this the big D. That's our detector circuit. Pulls that signal in. I'm simplifying because we're going to get a little more advanced as we go through. And an amplifier adds more power or amplifies that signal. Then various filter signals or circuits, we'll put an F in here. They strip away what we don't want. And finally, we get audio in the speaker of the radio, which was the same audio that came in from the transmitter. That's how the whole trick is done. You can think of the radio as a pair. A radio and a transmitter and a receiver are halves of a worldwide or a giant transformer. Now, to be fair, that's not exactly right, but it's based on the same principles. So I'm going to stop sharing this. We're going to go back to the book, and now I'm going to want you to keep that in mind because later on in the class, we're going to be utilizing that in greater detail. But that concept should make it a little easier to understand what a radio wave is. An electromagnetic field is dragging along electrons, and the electrons flow. But it's not the electrons that, well, at a transmitter side, the electrons flow through a wire, create a magnetic field, and the magnetic field drags the electrons through the metal of the antenna to create a signal inside or a wave inside the antenna, and that wave is what ultimately we modify, amplify, filter. Well, first we detect, and then we ultimately end up with a reproduction of the original information put in at the transmitter. We'll go into that in greater detail in the future. I'm going to come back to it, but I want you to always think everything here, think of your radio transmitter and radio receiver as two parts of a giant transformer. It's probably the easiest concept defining it. Now, in chapter 2, I want you guys got to start early getting familiar with this because it's going to come in handy. We're going to be using throughout the rest of this class the international metric units of measurement. So learn them the best you can. You won't use all of them. So bear with me, I'll tell you the most common ones you'll use. They are all multiples of 10. In frequency, we use kilohertz, megahertz, gigahertz. It's very doubtful you'll ever use terahertz. So a kilohertz is 1,000 hertz, or 1,000, I'm sorry, 1,000, yeah, hertz. A hertz is one wave. Did I cover that last week? What a wave is? Anybody? Did I cover a wave? Did I show you a wave and cover what it is? So
Yes,
learn
sir.
these units, because radio frequencies are generally from kilohertz through gigahertz. And a kilohertz is 1,000 hertz. A megahertz is 1,000,000 hertz. A gigahertz is 1,000,000,000 hertz, and that means it's very painful. I'm being humorous, I hope. On the flip side, the tiny stuff, we're going to deal with stuff that's such as values of inductors and capacitors. When we get to it, they're going to be in tiny numbers like milli, micro, and nano, and pico. We, for example, will talk about a microfarad. We might, oh, I'm sorry. I'll go back in a minute. I forgot. We might go microfarad. We might be a pico microfarad for capacitor values. Have a rough idea what they are. Look at this chart. Try to remember how it increments. You'll also find large numbers for resistors. A standard unit of measure for a resistor is an ohm, but it isn't unusual to use 1,000 ohms, which is 1 kilo ohm resistor, or 1,000,000 ohms, a mega ohm resistor. So you need to know these, and this chart, table 2.1, I highly suggest that you study it carefully and get familiar with at least from the base unit, which is the base unit would be right in between. Let me put a line through there. I think I can. Nope, I can't. Won't let me. The base unit would be in between deca and deci. Deca right here is 10 times the base unit. Deci is a tenth of the base unit. So if we were talking anything metric system, whether it's electrical or even if you buy I don't want to use drug measurements, so I'll avoid that. But if you buy a soda pop and a metric system, you might buy a liter. But when you fill your car up with gas, you might fill your car up with, well, if it was a big truck, 100 liters, which is a hectoliter. Or you might get 10 liters, which is a decameter. If you wanted to bake a cake and you needed a tenth of a liter, I'm sorry, did I say liter? I hope I did. If you wanted a tenth of a liter of say vanilla, well, you would put a deciliter of vanilla in. And if you're going to make nitroglycerin, don't make more than a few millimeters or milliliters, because that's enough to pretty much do yourself terrible damage. And it's a world of pain you don't want to get into. I'm, of course, joking. Okay. All right, I'm going to start again. I'm going to share screen again. Now, this is from the question and answer book, not your book. This is just the question and answers published for the purpose of both teaching and for the VECUs, but you can buy this if you want, but everything on the question and answer book is in your book. So it's redundant. But this chapter 2 covers units of measure, and I wanted to start here because I started on this. I'm going to go a little more in depth because it's that critical. So, for example, T5B1, the very first question, asks the question, how many milliamperes is 1.5 amperes? So let's go to the book and look at the chart in the book. Where did it go? Oh, there it is. It's really not cooperating today. There we go. So it wants to know how many milliamperes, and a milliampere is 0.001 of the base unit. The base unit in this case is ampere, which ampere is the unit of measure for current. Current is the flow of electrons through a conductor or a circuit. So it says, how many, in the question, how many milliamperes are in 1.5 amps? Well, as I said, there's 0.001 or 10 to the minus 3. But the easy way to figure this out is the first number here. If it was 0.1, it'd be a tenth, a hundredth, a thousandth. So it's a thousandth of an ampere is a milliampere. So if we had 1.5 amperes, it'd be 1,000 times 1.5. So let's go back to the question, see if that's right. 1,000 times 1.5. Oh, that's not the question. Here we go. 1,000 times 1.5. Oh, there it is answer C. 1,500 milliamperes is 1.5 amperes. The next question it asks here is, which is equal to 1,500,000 hertz? Well, it asks 1,500 kilohertz, 1,500 megahertz. Well, let's figure this out easy. 1,500 kilohertz. Well, a kilohertz is 1,000 hertz. And if we put 1,500 and divided it into this, we'd get 1,000. So 1,000 times 1,500. So a kilohertz, this is 1,000. So boom, we take this last, I don't know if I can undo it. No, I can't. Come on. Anyways, so we take this last 3 digits off. We got 1,500 kilohertz. It would also be 1.5 megahertz. And if we went to gigahertz, you divide again by 1,000 more. So if a kilohertz is 1,000 hertz, and you wanted to know how many kilohertz this is, you divide by 1,000. If this is, if you want to divide by 100,000, you'll find out how many megahertz it is. You'll be doing this a lot in your head as ham radio operators, because we deal with frequencies all the time. For example, you'll be dealing with frequencies that are maybe, let's say, 73, let's go a little lower, 72 kilohertz or 7.2 megahertz. Or you'll be dealing with frequencies like 50 megahertz. Well, if you wanted it in kilohertz, it'd be 1,000 instead of uh 50, you'd multiply it by 1,000. It'd be 1,000 larger numerically, not in total value. So instead of representing it by millions, you want to represent it by thousands. So that's what you need to do in all of these. So let's go back to that chart. These questions continue on, by the way. There are a bunch of them. All of T5 is all about, I'm not going to cover all of them because some of them, but they're all about units of measure and doing basic conversions. Now, some of them, like this, we're going to cover further on. They won't show up in chapter 2. They show up later. T5B, T5A is for chapter 2. So let me get back to the book. All right, moving along. That's why I want you to keep this chart. I would even print a copy or Xerox it to have it handy. Okay. Now, like I said, I discussed what a wave is and what frequency is, I hope. And this chart here is a pretty good representation. Keep in mind a wave is three-dimensional. It's like a circular shape of this. You're looking at it cut down the side, down the edge. This discusses, in this part of the chapter, it discusses the relationship between frequencies. We have something we call harmonics, harmonic frequencies. I can't do it in this drawing, but if you took this signal right here, starts at the same place. Well, imagine imagine it starts here, but it goes back and forth twice in the same distance of this. That's a second harmonic of a frequency. Goes back and forth 3 times, it's a third harmonic. These relationships have a lot to do with each other. Later on in the book, when we're talking about antennas and radiating signals, this is very important to grasp. I will be covering this in far greater detail, but for now, read this through just as it is. Okay, and I want to get out of this drawing. Don't worry if I jump around on you, because some of this I'm really going to come back for. Another concept you got to understand is waves and how they are in phase with each other. When we get to the point where we're talking about how antennas work effectively, the goal is to get a wave cleanly off the antenna and radiating the wave out. But in physics, for every forward action, there's a reverse action. Same is true of waves. Waves are a part of physics. So for whatever wave we push forward, at least a little bit of a counter wave is going to bounce back. Whenever you think of waves, think of water in the pool. When it gets to the edge of the pool, the wave is going to hit that edge. The wave will probably splash out of the pool if it's strong enough, but some ripple is going to come back. If that ripple comes back in what we call out of phase, then it clashes with the wave. If it comes 100% out of phase, it wipes out the wave. Sometimes in radio electronics, we take advantage of this in order to get rid of unwanted waves. But we don't want to do that at our antennas, for example. And this is why we have a concept we're going to eventually get to, matching an antenna and how an antenna works physically to send a wave off, and even how it receives a wave. We don't want crashing waves crashing into each other. So when you get to this part on phase, and it talks about how, well, when it talks about every cycle signal has the same basic shape, and it says a cycle is called a phase. If you've got a forward phase and a reverse phase, you don't want them crashing into each other. If the waves crash into each other harsh enough, they stop each other. And in fact, there are electrical devices that can make a room quiet by making waves that clash with the sound waves so that the sound waves can't travel. Same happens in radio. And we're going to cover that in the future. We're not going to worry about it too much. Okay. Radio spectrum. I want to bring this chart up, not this one, the other one. Oh, come on. Here we go. Wish I could blow this up bigger. I can't. It's in your books. Let's take a real good close look at this. Don't forget this chart. This will help you to visualize where everything is in a radio spectrum. We have very low waves, medium waves, high frequency waves, VHF, very high frequency wave, ultra high frequency wave, super high frequency wave, extra high frequency wave, and it goes on. We seldom use this high up yet, but you notice that AM broadcasted in the medium waves, pretty much short waves or the HF portion of ham radio bands are in the HF waves. It shows you TV, FM, and by the way, a lot of mobile is in the VHF spectrum. And more of the VHF spectrum is used for TV and mobile. Okay. And as you get closer to the super high frequency, you start shoving in the cell phone frequencies. But our ham frequency, our bands are pretty much all in here as well. The chart I told you about, and I'm going to unshare this. No, not yet. I'll do that after the next break. The chart I keep telling you about to keep handy, the band plan or the band chart, the ARRL band chart. And I will always stress that chart. I know I showed it to you last week. That chart is just the ham frequencies within these divisions of the spectrum. I don't know who got to pick these names or how they're defined. I know why they are. And the book will tell you about, where the AM band is, where the effect. You know what? I'll stop and we'll do that now. So it's easier to grasp this concept. Let me share. Let me open the screen, the band plan. There we go. And I am going to share screen. Where is it? Didn't pop up. Story of my life. Hold on. Still doesn't want to work. Okay. Try this here. Oh, hold on. Oh, that's not going to work. Tell you what, I'll get to it after break. If it doesn't want to cooperate, well, we'll see what happens now. All right, I got it. So I'm going to share the screen with you. We're going to discuss this. That's ARRL band plan scheme. This amateur band, chart. It's not really the band plan. But these are the frequencies we hams have allocated in the United States to us. Of course, each one of these represents a ham radio band, but the part I'm going to get to today is that from 80 meters here, or roughly 3.5 megahertz, through 10 meters, which is roughly 28.3 megahertz. That is the spectrum that we're all within the spectrum that the chart in the book I showed you earlier refers to as the HF spectrum. The frequencies from 6 meters to 2 meters, or to 1.25 meters, or 50 megahertz all the way up to the ham band of 2.9 megahertz. That spectrum falls within what is defined as VHF. The next two bands here fall in the spectrum of UHF. And this 1.2 gigahertz band, or 1240 megahertz band, the 23 centimeter band, it's all the same. This is on the edge of super high frequency. The stuff in the chart down here gets into the extra high frequency, but like I told you, I think in the past, you can freely use these bands. They're available, but they're pretty experimental. You're not going to find a lot of off-the-shelf stuff for it. So if you haven't already made a copy of this, go to the ARRL's website and download it. It's in your book, but it's in black and white in your book. I think it's in chapter 1. Okay, I'll go back to the book. So what we want to do is get a understanding of where these things lie. Now, I told you that from roughly 3 megahertz, I'm sorry, from 300 kilohertz to, no, I don't want that. I was right. From 3 megahertz, I was saying it right, where the 80 meter band is just above this at 3.5 megahertz, to 28 megahertz, which is the 10 meter band. Those were all those on the chart, on the ARRL chart, are all within this HF portion of the band. I also showed you how 50 megahertz, or the 6 meter band, and the 144 megahertz band, 2 meters, or the 220 1.25 meter band, they fit right in here. Now, the 430 mega, 420, 430, 440, all the way to 450, it's a real big band. The or 70 centimeter band, as we call it. Those frequencies fit right in this ultra high frequency range. So do, if you look at this, our 800 megahertz band, and actually so does our 1.2 gigahertz band, but it's starting to get closer to the ultra high frequencies. So I want you to know this, because you're going to have to reference this. It's going to ask you, what VHF frequency do you have privileges on right above the 10 meter band, or something similar to that? Well, the next band up, that's VHF, or what's the lowest VHF frequency you have privileges on? Well, it's going to be in the 50 megahertz band, and that band, by the chart that I showed you, you'll see goes from 50.0 to 54 megahertz. That is UHF. I'm sorry, that is VHF, because it is higher than 30 megahertz, but lower than 300. Don't worry that you don't memorize this right off the bat. Just plug with it. Eventually, I'm going to teach you some secrets to keep it in mind easier. All right. I'm going to share with you a screen and we're going to discuss the radio spectrum for a little bit. I'm not going to go back to book for a moment so that we can cover this. Let me see. Where did it go? Oh, I think it's here. Is it? Nope, that's not it. See if I drew this drawing. Hang on a minute, everybody. Cancel this. Let's stop share. All right, let's see where I drew the drawing. Here it is. And so it's here. So we'll reduce the size of it. Here we go. I'll share a screen with you. There we go. All right, I'm going to do some drawing with you. We're going to cover this. And let me open this up a little. Here we go. When radio first started, when the world of radio was new, they originally made noise everywhere, but they really only knew how to receive right around 200 meters, or where the AM broadcast band is now. And that was below about 1600 kilohertz. And everything above it, all the rest of this stuff, they had no idea what to do with it. It was all junk we didn't know what to do with, but roughly around 200 megahertz. I'm sorry, roughly around um, uh, roughly around 1.5 kilohertz, and they knew what to do with this stuff here. And hams, when we first started transmitting audio and so on, we were able to discriminate. Unlike the previous Morse code, we could discriminate all this, but the rest of this stuff we didn't know what to do with. We couldn't do anything with it. So this became the medium frequencies. Then they say, oh, why don't you guys play with this other stuff? You know, all this stuff here, you guys take that, go to work with it, see what you can do. Of course, the hams knew we were getting shafted, but, you know, hey, that's where the broadcast band went. So hams first, you learned how to use a little segment right here. It was right next to the AM broadcast band. It isn't 200 meters, it's around 160 meters. It goes from 1.8 to, I think I said 1.8 kilohertz, I meant 1.8 megahertz. It goes from 1.8 megahertz, or about 1800 kilohertz, to 2000. And this became our 160 meter band. I'm not going to worry about labeling it. So next, we started playing with a little section of the band, spectrum, I mean, right next door, a little ways up. We had this chunk, and it's around 3.5 megahertz. It's the 80 meter band. And we did this, or we continued all the way up to around just under 30 megahertz. And these were all the ham bands back then. Now, in between time, they got cut up and so on. So we got left with segments. All right. But this big spot in the middle was higher than everything else they knew how to use. So the medium waves were here. The low stuff down here, they didn't know what to do with it either, but nobody cared. And hams had shown the world, well, we can use the higher frequencies. But after about 30 megahertz, they couldn't really, they didn't know how to use those frequencies above that. They didn't have technology for fast enough devices to switch back and forth to create an oscillation fast enough. So everything above that was useless, but we hams had it anyways. But then they chopped all this up on us. When they did, they said, okay, guys, we're chopping up all the stuff down below. All the stuff above it is yours. And they did. Well, we figured out how to use a portion in here about in the 1940s. And it was above where the HF was. So they called this the very high frequencies. And we got all the way up to like, 144 megahertz, 200 megahertz. And once we figured out how to use it, they chopped some of that up and they left us with our VHF bands. And hams kept playing with all the stuff left over on the top, which is cool. Now we discovered how to use UHF bands. Well, the first people that wanted a chunk of that was the TV people. Originally, TVs only had VHF stations. Sometime in the 1960s, we hams had gotten successful at proving all the rest of these frequencies might work. And technical advances came in the terms of electronics. So that's when we started getting UHF television channels. In the meantime, in our interim, by the way, I forgot to mention that the FM broadcast band got shoved in the VHF spectrum. And so we started losing some of that portion that was UHF. And everything above it that was left is the super high frequencies. So now you understand how they got named. If back in the day, when they didn't know how to use all this, they had a concept of the fact that they would be one day usable, they might not have called this medium frequencies. They might have moved the medium frequencies somewhere in the middle, but it's closer to the bottom of the, it's just the way it is. So that makes sense if you understand the history. Going back to the book. So the book starts to tell you about just the concepts I'm telling you about. And we need to discuss it. First of all, like it says in the book, from 535 kilohertz to 1700 kilohertz, the 200 meter band effectively became the broadcast AM band. Once it was demonstrated that we could use frequencies in the UH or VHF spectrum, 88 to 108 megahertz was assigned to the FM broadcast band. And we hams got left pieces in between, which is a normal way things occur. Today, there are microwave frequencies. It talks about microwave ovens. And I'll tell you about that a little more later on. But All these portions of the band got chopped up and we got what's left. And this has been a normal progression, and it will continue to be, because the world doesn't have anything much more expensive than radio spectrum. Every single frequency we use is worth millions of dollars. An AM broadcast station gets to use its frequency, its exclusive frequency, one frequency. Same with a commercial station. They get one frequency, costs them millions of dollars a year to use and retain that frequency. We get ours for the price of, we get them for free. $35 every 10 years. Pretty good bargain, you ask me. All right. Now, when an AM signal is generated, it talks about this in figure 2.4. I want to explain what signal 2.4 is, or figure 2.4. When an AM broadcast signal is sent out, it's sent out on a center frequency. I'm going to use this as an example right here. And the signal has a width to itself. The width, or how wide of any spectrum is being used, comes under a general term, bandwidth. A radio transmitter signal has a bandwidth. The width of an entire band is its bandwidth for the band. And you have to be aware of various characteristics of your signal. Every signal will have a width. A signal will have an amplitude. That is how strong or how powerful, basically how much voltage is in the signal as it travels out in the air in a way. It's the strength of the wave, okay? Weaker signals are smaller amplitude signals than higher signals. Now, somewhere in the background, there's probably noise too, so you need your signal to be higher than the noise. This signal, if this is the noise level, by the way, this is not what this chart is meant to be, but if this signal had a noise level this high on it, on the same frequency, you would not hear this signal. It's below the noise. This signal would be louder than the noise, so you can actually discriminate out the noise or chop it out. We have ways to do that. And this signal is so strong, the noise might be insignificant. And if they were all on the same frequency, depending on the mode of operation, this one might win, might not. Depends on a lot of other factors, but we'll cover that in the future weeks. Okay. So a signal that you're transmitting has, let me go back, has a bandwidth. It has a peak or amplitude. And the next thing it does is it has intelligence. It's carrying information. The information it's carrying is the audio or digital signal that you're trying to transmit. Come on. There we go. And receive. I'm going to skip over some of this because when I cover it, I'll get to it. Now, I also last week rather quickly defined for you what a wavelength is. And I'd like you to remember that a wavelength is a signal, or a wavelength is the distance that a signal travels in 1 second. All wavelengths, all waves, radio waves travel at speed of light. Radio waves particularly, I mean. But if a frequency is very high, it travels a very short distance in one cycle. If a frequency is very low, it travels a much longer distance. And so a wavelength is a distance that a wave goes from one point through its opposite peak and back to where you reference it again in 1 second. And I think I told you that the wavelength is equal to 300, which is the speed of light, divided by the frequency. It will give you the I'm saying that wrong. If you want to know the wavelength, you take the speed of light and divide it by the frequency. So if your frequency is 100 megahertz, not a ham band, but this is easy math, and you want to know what the wavelength is, and the wavelength reflects the dimensions of the antennas that work for the frequency, as well as what we were referring to as the various bands, like 80 meter and 160 meter, 200 meters. Those are all wavelengths. So if we wanted to know the wavelength of a 100 megahertz frequency, we'd take 300 divided by 100, and we get 3. The 300 or the 3 meter band is roughly 100 megahertz, where the AM or FM broadcast band is. 144 megahertz is a little above that. The 140 megahertz band is the 2 meters band, that what we call a 2 meter band. Roughly, if you divide 140 or 150 megahertz into 300, you're going to get 2. And this is going to come in handy when we're talking about antenna design. Now, I'm going to take a little break. All right, I'm back, and we'll get started. I'm going to share with you a screen right now, a little drawing I've had to finally find. Actually, I modified it. And hopefully this will help you understand. And in the future, I'm going to be referring to things like this. Oh gosh, come back here. Where'd you go? It's not what I want. There we go. Hopefully make this bigger and easier to see. All right. What this drawing represents would be a type of antenna called a dipole, 2-element antenna. And think of this as being one side of it, and this is the other side. It's a very common antenna for amateur radio. And the 2 wires coming off of it would essentially are a simplified version of a coax going back to the radio. What I want to explain is why fundamentally wavelength is so important in amateur radio. If this is a wave on this antenna, this black wave, you notice that this wave is at 0 at the end here. It passes through 0 in the middle. And at the other end of the antenna, it's at 0. At these points in the wave, these are nulls. or to put it mildly, there's no voltage presence at the end and at the middle. This wave will radiate off very efficiently. But if a wave is just starting in the middle of this antenna, and then it's trying to leave the antenna at its maximum voltage, that doesn't work out. What happens when that occurs, and we're going to cover this in the future, what happens when that occurs is that this wave is going to generate a wave back. And that wave back is going to wipe out any wave forward. Don't quite have that drawn properly. It should be like this. And it should be flipped. And I don't know how to flip this thing. Let's see if I can get it to do it. Nope, that ain't going to do it. So wavelength is an important principle of radio. You need the electromagnetic wave to travel the distance it travels along the antenna. You need it to travel it in a precise manner. The closer you get to this arrangement, the better the antenna will function for transmitting. We'll discuss receiving antennas as well, but right now, the concept of transmitting antennas, this is extremely important. So the frequency of the wave determines what this wavelength is. That means the frequency of the wave, that if it determines that wavelength, it is that wavelength that determines what the dimensions of the antenna must be to be most efficient. Now, you can transmit on all sorts of antennas, but you want your signal all to get out, you got to be closer to this black wave, not the red one. All right, I'm going to unshare that. We're going to go back to the book. And let's share screen, go back to the book. Here it is. So that's why this distance traveled by the wave is so important. By the way, you can use this formula to help you calculate the dimensions of an antenna. We're going to discuss that later in the class. I'm also going to give you a formula that works in feet and inches. Well, feet, but it's a lot easier to deal with. So, so that's why this formula and my discussing it is so important to you. Keep this formula in mind. You're going to use it throughout your career as a ham. If you take 300 divided by the frequency, if the frequency is in megahertz, you're going to get the wavelength in meters. You need that to determine, for example, a quarter wavelength antenna or a half wavelength antenna, etc. Obviously, if you wanted a quarter wavelength antenna, you would then just divide it by 4. If you wanted a half wavelength antenna, you would divide it by a half. We'll cover that in greater detail in the future. A variant of this frequency, of this formula, is instead of dividing the frequency into 300, if you divide it into 468, the answer will be in feet. It'll be in US measurement. We'll get to that when we get to antennas. All right, I've covered a lot of this, and I think it's pretty obvious. Radio equipment basic. Before you, I've never been thrilled with this, but I want to do a little better explanation, and they do this block diagram here. In the early days when we started in amateur radio, people before me, truthfully, my first radio station was like this, but because it was homebrew. Basically, we had a separate transmitter, a separate receiver, and a transmit switch. Transmit switch switched the transmitter when we transmitted to the antenna, and a separate relay or a separate element of the relay switched the transmitter on to transmit, and our signal went out. Then we threw the switch back to receive. The transmitter got turned off a transmit in idle, and the transmit switch hooked the receiver up to the receiver. Inside a modern transceiver, this is done for you. There's not a separate switch to do this or set of switches. There's electronics doing this for you. You cannot transmit and receive on the same antenna at the same time on the same frequency. You can't even do it on different frequencies without some very extensive equipment to protect the receiver and the transmitter. We'll discuss that in the future as well. Okay. Now I want to talk about antennas for receiving. I've told you how an antenna, how a receiver transmits. And I'm not going to get to that just yet. So I'm going to stop the share just for a minute, not to be confusing. A receiving antenna is different than the transmit antenna. And I have a drawing here. Guess I'll make one. Okay. Screen I'm sharing. I can't even see that screen. Where is it? Is this it? Yeah. Okay, are you guys seeing this paint screen? Because I can't see you guys right this minute. Yep, I got a thumbs up. Okay. If you remember, I told you that the transmitter sends these waves, electromagnetic waves out, and they do so in a spherical or circular orientation. It's not what I want. Yeah, it doesn't matter. They're sending out waves. Now, if these waves wrap around a wire, well, these waves, they're going to send electrons moving. Along the wire as they cross the wire. The more lines of electromagnetic flux that intersect a receiving antenna, actually, the more energy or the higher the amplitude of the signal the receiver is going to get. So a receiving antenna technically is much better the longer it is. Up to a point, there's some physics involved, but generally you can think of it from the concept that the more of these waves you get cutting through, the more electrons being pushed, and the higher the amplitude that's in that drawing, the higher the amplitude of the signal going into the receiver. What's important to keep in mind is that a transmitting antenna is optimum for transmitting. A receiving antenna is optimum for receiving. But just as I had in this drawing for you, oops, I didn't save it, but I'll pick another drawing that's similar. A transmitting antenna might be designed. This is a particular antenna. I'll discuss it later in the class. But a transmitting antenna is designed to work at some frequency or sometimes with special circuits at different frequencies. But usually a transmitting antenna really only works best at a receiving antenna. It happens to be that when you have the perfect transmitting balanced antenna, you get a pretty darn good cut across the electromagnetic waves, and they're lined up better for the receiver. And they work pretty good, but it's not the best antenna for receiving. Longer multiples of this, in other words, if we kept adding on longer and longer in the same lengths that are already here, they would get better and better and better. The reception would get stronger and stronger to a certain point. It's a point of what they call diminishing returns. And that's why you'll find in like old AM radios, a big wind of an antenna. It's wound around a core, or it's a big loop of wires wrapped in a spiral, because they want to intersect as many of the lines of electromagnetic wave or flux as they can. And they actually have to calculate out exactly the dimensions of how that works to do it most efficiently. So if we're designing an antenna for transmitting, let me stop the share. We're going to want an antenna that works best. If we're going to design it and gets the signal off the best. Antenna is not designed, or receiving antenna is not designed to get the signal off the wire. It's intended to bring it into or onto the wire. It's a different concept, different purpose. So here's a rule number one I want you to never forget. All amateur radio antennas are a compromise. Unless you're willing to have one transmit, one receive antenna for every single frequency you use, and switch back and forth between them for every individual frequency you operate at, pretty close to that. Every amateur radio antenna is a compromise. If anybody ever tells you this is the best antenna for amateur radio, either they're a con man trying to sell you true garbage, or they don't know what they're talking about. So, going back to the book. Every time I do this share, I never know what I'm going to see. And right now, I don't see the book. I'll tell you what. Let's try this again. Find out what happened to this. There we go. Share screen. There it is. Okay, back to the book. So, in amateur radio, the first and most important thing I want you to know about equipment. The whole trick is done by the quality of antenna, and next by the quality of antenna, and by next the quality of antenna. It's not power. It's not, well, it's a little bit location, but the most important thing is the least expensive. Antennas don't have to be complicated. They don't have to be expensive. They don't have to be some fancy thing some guy tells you is the greatest thing, some sliced bread, because probably not. You just have to be right for the use you're using. They have to be designed properly and used properly. By the end of this class, you'll be able to do this with no problem. Okay. Now, in the tech class license, one of the great things we've had since 1970, about 1970, 1969, is we started installing amateur radio repeaters around the country. A repeater allowed us to use the VHF and UHF frequencies and then repeat them so that they weren't just useful to us for a very short line of sight distance, but rather to give us area-wide use of the radio communications. And the way that a repeater works, I don't know, yeah, here's the drawing. The way that a repeater works is you have a transmitter and you have a receiver. The transmitter is on one frequency. That's the frequency that the repeater transmits on and the user ham listens to. The receiver at the repeater listens on a frequency and it takes the audio from whatever it hears on that frequency, which is the frequency that the user ham transmits on, and it injects that into the transmitter so that the transmitter sends it back out at the same time. And so everyone listening in is listening to the transmitter. Everyone, when they transmit, is transmitting on a repeater frequency, and an enormously complex device in the middle called a duplexer, usually something we call cavity filters, that require precision tuning and alignment, allow for the transmitter frequency to go out and not get into the receiver, and allow this all to work. Repeaters also have automatic controls on them, identifiers, and many other options. And believe it or not, when we first started, we didn't have any of that. We first started with repeaters. We had a guy throwing a transmit switch, no duplexer, and a receiver. So he had to switch back and forth, or we moved the transmitter antenna way off, far away from the receiver antenna. And by doing that, we still had a guy transmitter switching and repeater switching. Had to have somebody stationed as a control operator for the repeater on the location all the time. Eventually, the FCC accepted that we could make it work, and we demonstrated that, got permission and demonstrated it. And eventually, the FCC said, okay, you can go automatic control. And there's all sorts of rules about it you're going to learn about coming up. At least you'll learn about some of them. So the way a repeater works, a repeater will have a frequency, a repeater frequency, that will define what the frequency is that you as the ham will listen to when you're using a repeater. The repeater will have a frequency offset. The offset is how far away, plus or minus, in the radio spectrum you should transmit. And UHF and VHF radios for AM radio nowadays are designed so that the repeaters or the radios can transmit to the repeater, receive on different on the offset frequency. Later in the class, we'll cover this in greater detail. Don't get overly concerned with any of this. But that's how we use repeaters. A little info. Originally, we intended repeaters, solely for the purpose of mobile operation. So we defined or set the definition. At the time, the most common or highest powered mobile radios we usually have was around 20 watts. We defined repeaters to cover an area. We installed them so that area would permit accessing the repeater with a 20-watt mobile radio, usually a 50-mile range. And we tried to make that standard. Wasn't always possible. Sometimes we beat it. Sometimes we couldn't quite get it. Today, our repeaters are pretty good. Sometimes a lot better than that. So it's not unusual in many areas to have wide area repeaters that you could probably work with 5 watts for 30 miles. Our old repeaters couldn't do that. And if you were in a high location and had outside antenna, you might do better. The other thing about repeaters to know is we've entered the world of digital radio, not just FM. And in digital radio is digitizing the audio and then sending it not as audio, but as a digitized signal over the air, which a little computer in the radio converts back into audio for you again. It basically isn't a digital to analog conversion. Digital repeaters allow us to send the audio from a digital signal as a digitized signal across the internet. And by going across the internet, we can make repeaters accessible, say via the internet from your cell phone. So you could use your cell phone to pull up an app, and that app could link you into a website. That website, most of this is transparent to you. That website will allow you to link to whatever repeater you want and operate through it just like you were on your two-way radio. It also permits us to link repeaters to repeaters across the internet. So we can link a repeater, say, in Chicago to a repeater in LA, and people driving around in the range of the repeater in Chicago can talk to people in LA. In fact, to be more precise, the farthest I have worked in such an arrangement, I have talked on repeaters here in Michigan to people in Europe and Asia because of links from their repeaters to ours. And another example is I'm involved with a group that has put together a group of repeaters along the east coast of Michigan. And our repeater links provide repeaters that are linked to each other from Sandusky, Ohio, all the way along the east side of the state of Michigan to Sault Ste. Marie in the Upper Peninsula. We have repeaters all the way in between, and it's not unusual for me in the morning to run out, get a cup of coffee, and talk to hams anywhere along that length. All right, we're going to take a little break, and I'll stop the share. Are there any questions at this moment? Okay, basically we are done with chapter 2. There are parts I will come back to when they're more applicable for you. I want you to by next week read chapter 3, but we're going to go through questions and answers pertinent to chapter 1 and 2 day after tomorrow.